Hey guys, so here's the notes for 7.3. We have growth and decay word problems. Now on your notes, if you printed out the notes, the Unit 5 notes, or you grab them at the LMC, you might see this as labeled 7.1 to 7.2, growth and decay word problems. We're on the same section. I just wanted to recall it 7.3, okay? Okay, so let's talk about exponential growth and exponential decay with our models. Now we've talked about already with growth, we said if we have in the form of y equals a times b to the x, if our b is greater than 1, that is a growth. Now when we represent it with a model, we're going to have it as the form of y equals a times 1 plus r to the t. Now let's talk about what each of these values represent. Of course, y is your final amount. A is going to represent the initial amount. R is your rate, and we have to do it as a decimal. So it'll give you it as a percentage, but you have to change it to a decimal. And T represents time, okay? Now, if you think about it, if we take whatever our rate is, of course, change it to a decimal and add it to 1, it's going to be a number greater than 1. So that's why it's exponential growth. Now, for our other exponential decay, remember that is going to be our b value that is in between 0 and 1. So when we have our formula, y equals a times 1 minus r, where all the variables are exactly the same. So y is your final amount, a is your initial amount, r is going to be your rate as a decimal, and t represents time. So we take our rate, change it into a decimal, and do 1 minus that. That value is going to be in between 0 and 1. So that's why it is a decay. So with exponential growth, anytime to know, oh, is this a growth or decay problem, we'll kind of look at the context. See if something is increasing or growing. While decay, if something is decreasing or decaying, of course, you're going to use the exponential decay. Okay, make sure you have this written down, so if you got to pause the video to do so, make sure. We're going to go ahead and do some example problems. Okay, number 1, it says the value of a car y can be approximated by the model y equals 25 times 0.85 to the x, where x is the number of years since the car was new. Now, first we need to tell whether the model represents growth or decay. Well, remember in the form of y equals a times b to the x, b can represent either our growth or decay. In this case, our b value is 0.85. Now, is that in between 0 and 1, or is that greater than 1? Well, that's in between. So that means we are going to have a decay. Okay. So our model represents decay, since our b value is in between 0 and 1. Now, identify the annual percent increase or decrease in the value of the car. Well, because we're decaying, we are decreasing. So remember in the form for our decay model, it's y equals a times 1 minus r to the t. Now, they have given us our form of y equals, I think it was about 25, okay, 25, okay. So with the 1 minus r, we can actually set that equal to 0.85 and really figure out, well, what is the r value, okay? So I'm going to go ahead and do 1 minus r, or some of you might have just like, I know how to do this in my head, which that is fine, because you can also think 1 minus what will give us our 0.85. That's another way of thinking about it, okay? So you can do this algebraically or just do it in your head. So I'm going to subtract 1 from both sides. I get negative r equals negative 0.5. Divide by both sides by negative 1. So I get r equals 0.5. Now it does ask us the annual percent, so I do need to change my 0.15 into a percentage. Now, how do I do that? Remember, we just moved the decimal over 2 places to the right. So that's going to be 15%. So a 15% decrease. And that'll be your answer there. Okay, now let's go ahead and work on the problems where we are creating the model and using it to find the final amount. Let's try example 2. So it says in 1970, the population of Kern County, California, where Bakersfield is located, was about 330,000. And from 1970 to 2000, the county population grew at an average annual rate of about 2.4%. Now, our first thing is we need to write an exponential model giving the population P of Kern County X years after 1970. So we're writing the model. Now, notice what we have to use for our variables, P and X. So instead of putting Y equals, we're actually going to have to do P equals, okay? Now, it says the county population grew. So is this going to be a growth or a decay model? It is going to be a growth because the population grew. So I have P equals, of course, then I know I'm going to have to do 1 plus R. Now, let's identify our A value, so the initial amount. So initially, the Kern County had a population of 330,000. That was our initial. Then we have 1 plus. Now, our rate is 2.4. But remember, we need to change this into a decimal. So to change it to a decimal, I need to move my decimal over 2 times to the left. So I'm really going to have 0.024. And then to the X. Now make sure, we do want to make sure that we combine our 1 and the 0.24, so simplify. So I have P equals 30,000 1.024 to the X. So this will be my model. So always simplify what's in those parentheses. Okay, now we're going to use our model to predict the number of people in Kern County in the year 2010. So the model we're using now, the idea is we're trying to find what the X is, because we are trying to find we're trying to find population, but we need to plug in a number in for X to represent that time. So we started in 1970, and now we're going to 2010. I'm going to go ahead and do 2010 minus 1970. Of course, if you want to plug that into your calculator, but that will give us 40. So I do 40 here. Now, all I have to do is plug this into my calculator, and then I'm good to go. Okay, so here's how we'll plug it in. So I have 330,000. Then I do parentheses 1.024, and then to the 40th power. And so this will be my answer. Now, the thing is, of course, if we're thinking about population, we definitely cannot have just 0.45. Now, how we're going to do this is we are actually going to round it like if we normally would. Anything basically 5 or higher, we would round up. Anything lower, we just round down. So that's going to be the same thing here. So we have, since we have 0.45, we're just going to go ahead and round down to the nearest whole number. And so that'll be 852,142. So that's going to be our final answer. So 52,142. And don't forget your label, since this is a word problem, and we're going to say people. Okay. So that would be my final answer there. Okay, let's go and do the next one. Okay, I actually would like you to do is pause this video and try this one on your own. Okay, let's see here. So we have a new snowmobile that costs $42,000. The value of the snowmobile decreases by 10% each year. So first you need to write an exponential model giving the snowmobile's value y after X years. So here we have to decide, once again, is this a growth or decay model? Well, in this case, when it was talking about the value of the snowmobile, it was decreasing. So that means we are going to have a decay model. So with the decay model, we're going to do 1 minus r. Now with our model, we are still going to use y and x, so that's the nice part. Now the snowmobile originally cost $4,200. And this is what happens with all, vehicles. They always decrease. This is what we call depreciation. So now I do 1 minus. Now our R here, we are at 10%. But remember, we're going to change that to a decimal. And how we do that is we move the decimal over 2 times to the left. So I basically get 0.10. So that 1 minus 0.10 to the x. Now we have to simplify what's inside the parentheses for our final answer. So I get 0.9 to the x. And that will be my model there. Now I'm going to use my model to estimate the value of the snowmobile after 3 years. So t, or in this case x, that's going to represent the years, or x is going to be 3. So I'm going to have y equals 4,200 times 0.9 to the third power. And then we can just plug this into our calculator. And we get $3,061.80. Now, because this is dealing with money, it is okay to get decimals. Now, with all money, you always round to 2 decimal places, or to the hundredths. So here, we're going to write, don't forget the $sign, because we're representing money, and we got the 80 cents. So here we didn't need to do any rounding because it was already to that tenth place, and we can use that as part of our answer. Okay, next we're going to be talking about compounding. And so that's going to be working with more of these types of models, but it'll be talking more with money-wise and how we can compound on the idea of interest.